everyone, this is Jeanne John from Government First Grade College KGF 3rd BSc. So on today's seminar, we have taken the third unit of the paper 8 quantum mechanics. Under that topic, we have taken Schrodinger's theory of quantum mechanics. So today we are going to derive the wave equation of Schrodinger's theory of the hydrogen atom. So let's move on to the derivation. So here we have the hydrogen atom. So we have the proton, electron. The proton is at the origin O and the electron with mass m and the charge of the electron E. So the electron is moving around the nucleus of the hydrogen atom of proton of mass capital M. So the proton of mass is equal to 1845 meters. Since it is equal to 1845 meters, the proton is at the origin, which is stationary. So here we have the r is the radius of the orbit. So the potential energy due to the Coulomb field is given by V of r is equal to minus E square divided by 4 pi square 4 pi epsilon naught. Take this equation as 1. So here V is called the potential energy and R is called the radius of the orbit. So V of R is equal to minus E square divided by 4 pi epsilon naught R. So let us consider this equation as 1. So next, Schrodinger's time independent wave equation is given by d square psi divided by dx square plus 8 pi square m divided by h square e minus v psi is equal to 0. Consider this equation as 2. So the time independent wave equation is given as d square psi divided by dx square plus 8 pi square m divided by h square into E minus V into psi is equal to 0. Consider this equation as 2. Now let us consider the position of the electron in the polar coordinates, which is represented by a diagram. So here we have the proton at the origin and electron at the point P, which makes the polar coordinates P of r, comma theta, comma phi, and it makes here the angles theta and phi. So now let us draw a line which joins OP dash and makes which has x, y and z. So here we have the spherical coordinates r, theta and phi, where r is the radius vector, theta is the polar angle and psi is the azimuthal. So the rectangular coordinates is given as x is equal to r sin theta cos phi, y is equal to r sin theta sin phi, z is equal to r cos theta, which is already known to us. So let us consider these rectangular coordinates as equation 3. So next let us write all the formulas for the polar coordinates for the radius vector, polar angle and azimuthal angle. So the radius vector r is equal to square root of x square plus y square plus z square. The polar angle theta is equal to cos inverse of z divided by r, and the azimuthal angle psi is equal to tan inverse of phi by x. So now let's move on to the next step, that is in spherical polar coordinates the Laplacian del square is given as half into dou by dou r into r square dou by dou r plus 1 by r square sin theta dou by dou theta into sin theta dou by dou theta plus 1 by r square sin theta dou square divided by dou phi square. So this is the spherical polar coordinates. In spherical polar coordinates, the Laplacian del square is given as this equation. So the Schrodinger's equation becomes 1 by r square dou by dou r into r square dou psi by dou r plus 1 by r square sin theta dou by dou theta into sin theta dou psi by dou theta plus 1 by r square sin theta dou square by psi dou square psi by dou phi square plus 8 pi square m h square E minus V psi is equal to 0. Consider this equation as phi. So, from this equation, from the fifth equation, we have V. Okay. So, we saw in the first equation, equation 1, the value of V. So, we are going to substitute that value of V in equation 5. Okay. So, we will be substituting it here and multiply the fifth equation by r square sin square theta. So, we get by multiplying and by substituting the value of V. So, we will be getting as r square sin square theta. So, r square and r square will get cancelled. So, we get sin square theta dou by dou r into dou square r square dou psi by dou r plus sin theta dou by dou theta, sin theta dou psi by dou theta plus dou square psi by dou phi square plus 8 pi square m r square sin square theta by h square. So, since we are multiplying r square sin square theta, we will be substituting here and e plus. So, minus into minus. We are having in first equation minus e. So, minus into minus become plus and it becomes e square divided by 4 pi epsilon naught r is equal to 0. So, let us consider this equation as 6. This is called a partial differential equation for the wave function psi of the electron of the hydrogen atom. So, now the wave functions psi 1 of r, psi 2 of theta and psi 3 of phi is dependent only on r, theta and phi. So, psi 1 of r is only dependent on the variable r, which is the polar coordinate. Psi 2 of theta is only dependent on theta. Psi 3 of phi is dependent only on phi. So, here we have psi of theta comma r comma phi is equal to psi 1 of r, psi 2 of theta and psi 3 of phi. So, let us consider this equation as 7. So, substituting 7 and 6. As we saw in the sixth equation, we are going to substitute the psi value in the equation 6 and divide that equation throughout by psi 1, psi 2, psi 3. And by rearranging, we get this equation. So, from this equation, in RHS, this r and theta are the functions of LHS psi. And psi is only the function of RHS psi. So, let us consider the RHS, that is minus 1 by psi 3 dou square psi by dou phi square. So let us consider this RHS as constant which is m1 square. So, solving this, we get d square psi by d phi square plus m1 square psi 3 is equal to 0. So, this, let us consider this equation as 9. This equation is known as the azimuthal equation. So, d square psi by d phi square plus m1 square psi 3 is equal to 0. So, now let us consider the equation 9, which is the azimuthal equation, and let us substitute the m1 square value which we saw in the azimuthal equation for the RHS of equation 9 in equation 8. Let us substitute the value of m1 square. So, after substituting, we get this equation, okay, which is 1 by psi 1 d by dr into r square d psi by dr plus 8 pi square m r square by h square into e plus e square by 4 pi epsilon naught r is equal to m1 square by sin theta minus 1 by psi 2 sin theta d by d theta sin theta d psi 2 by d theta. So, this is the equation we get after substituting the value. So, now here RHS of equation 8, let us write the RHS of equation 8, okay. So, this is called the polar equation, okay, and let us write the left hand side of the equation 8. This is called the radial equation. So, therefore, the Schrodinger theory of the wave equation is divided into 3 parts. First, we saw the azimuthal equation, and second, we saw the polar equation, which is obtained by substituting the value. So, the RHS of the equation 8 is considered to be the polar equation, and the radial equation is considered to be the RHS of the equation 8. So, again I repeat it, it is divided into 3 parts. First is the azimuthal equation, second is the polar, and third is the radial equation. Next, let us see the conditions for the 3 equations. First is the azimuthal, polar and the radial equation. First, let us consider the azimuthal equation. So, in the polynomial form, it is written as psi3 of phi is equal to a exponential of IML phi. So, here where ML, it takes the values 0, positive and negative. 0, plus or minus 1, plus or minus 2 until up to plus or minus L. So, here this L, which is the constant, it is called the magnetic quantum number of the hydrogen atom. L is the constant and it is called the magnetic quantum number of the hydrogen atom. Okay, this is about the azimuthal equation. Second, let's go to the polar equation. Let's see what are those conditions. So, this is the polar equation, what we see here. So, in a polynomial form, it is written as PL ML cos theta, where the ML, it takes a value 0, positive and as well as negative, as of the azimuthal equation. So, here ML takes the values 0, plus or minus 1, plus or minus 2 until up to plus or minus L. So, L is the constant, it is called the orbital quantum number. Next, let's go on to the radial equation. So, radial equation is given in equation 8. As associated, it is associated with the Langmuir polynomials ln L of R. ln L of R. So, this ln, this nth state is given by E of n, which is m divided by 2 bar h square into e square divided by 4 pi epsilon naught the whole square into 1 by n square is equal to minus m e to the power of 4 by 8 epsilon naught square h square into 1 by n square. So, this value is called is 13.6. If you calculate it, you will get 13.6 1 by n square e into v. So, this is the nth state, nth state of energy. So, here n is greater than or equal to L plus 1. So, this is about the radial equation. So, next let us see the 3 quantum number of the hydrogen atom. The first one is the total quantum number, second one is the orbital quantum number and third is the magnetic quantum number. In total quantum number, the n is equal to 1, 2, 3. And in orbital, it is L is equal to 0, 1, 2, 3. It takes the value 0, 1, 2, 3 up to n minus 1. And in magnetic quantum number, it is ML, that is equal to 0, plus or minus 1, plus or minus 2 up to plus or minus L. So, these are the 3 quantum number of hydrogen atom. And next, let's see the energy levels of the hydrogen atom. So, here it is given as the it is given the energy levels of the hydrogen atom as the number of values, as the n values increases, the energy levels are very closely spaced to n classical 10. This is the energy levels which is known as the Bose correspondence principle. So, this is about the hydrogen atom of the Schrodinger's theory. So, let us rewind what and all we have studied. First, we saw the hydrogen atom, and second, we saw the polar coordinates. How we can, in polar coordinates, through the diagram, we saw how could we solve the equations, and next we solved each and every equation, Schrodinger's wave equation and so on. Next, we found the 3 equations. First is the azimuthal, polar and the radial, and then we saw the conditions. And last, we have seen the energy levels. So, this is about the Schrodinger's theory of the hydrogen atom. This is the end of our topic. Thank you.